Number 4, this is a diver who dives off a platform and starts spinning, and while she's falling, she does something and she spins differently for a little while. We're given her initial spinning rate in radians per second. We're given her a moment of inertia in the beginning in kilograms meters squared, and then her new angular speed after she does something. She's either going to speed up or slow down, and which one of those she does depends on your particular numbers. We've got to find these things. So first we need to find her initial angular momentum, and that's really, so these are my numbers I used. Sorry, before I jump into this. This is her initial angular speed in radians per second. So she's not quite doing a full circle every second. Full circle would be 2 pi radians, and this isn't 2 pi. And this is her moment of inertia in the beginning, and then this is her angular speed after she does something, which is a little bit over 2 pi. So now she's over one rotation every second. Part A is just the angular momentum formula. Angular momentum equals moment of inertia times angular speed. And we know both the moment of inertia and the angular speed, multiply them together, and that gives you the answer. Part B is asking for her rotational kinetic energy in the beginning. And here you can just use the rotational kinetic energy formula, 1/2 I omega squared. I is her initial moment of inertia. Omega is her initial angular speed. Don't forget to square it. And when I do it, I get that. But you're going to get something different. Number 4, this is all number 4. The third part, or part C, what's her new moment of inertia after her angular speed changes? This is the law of conservation of angular momentum. Her angular momentum is not going to change during this. There's no net torque acting on her body. So momentum before equals momentum after. I can also write it as momentum before equals momentum after. This is just plugging in the formula for angular momentum. The initial angular momentum I've already calculated, 19.1. Her new angular momentum is going to be her new moment of inertia times her new angular speed. So I can just divide both sides by 6.35 and I get moment of inertia. And I didn't really answer it on here, but there are a couple of ways to do number 4. What does the diver do to cause this change in moment of inertia? So if the moment of inertia, the initial one is 4.29 and the final one is 3.01, that means she tucks in. The general form of moment of inertia is mr squared. And all the formulas for moment of inertia have r squared in there. So unless her mass is changing, if her moment of inertia is decreasing, that means her radius is decreasing, so she's tucking in. Another way to come up with the right answer here is to say, if she starts out rotating slowly and she is rotating faster in the end, that means she's tucking in too. It's like a figure skater pulling in the arms and speeding up. And the reason figure skater speeds up is partly because moment of inertia decreases and therefore angular speed increases, and it's partly because in pulling in your arms you do work on yourself more or less and speed yourself up. Number 5. Oops, I skipped a page. It's wasteful in this time of hoarding. Sorry, my computer went to sleep. See if I can wake it back up. Doesn't know me. Right here. Okay, finally recognized me. So number 5, this is the round object that's rolling up a hill, and we're given its radius, mass, initial translational velocity, and then we're given the value of x to use in determining moment of inertia. Moment of inertia is going to be x times mr squared, where x is the value given below. So here are my givens that I used for the radius of the object. It's really small. It's only 1 centimeter in radius, 2 centimeters in diameter. There's the mass, not very heavy. It's going pretty fast though. And then this is x, which means its moment of inertia is 0.16 mr squared. Now, this, in the broad sense, is a conservation of energy problem. So as it rolls up the hill, its total energy before equals its total energy after. Same total energy there and there. We're assuming no loss to friction or anything. In the beginning, the ball has a lot of kinetic energy and no potential energy. And when it gets to the top, it has potential energy but no kinetic energy. So expanding or substituting in the real values for these terms, I get kinetic energy is 1/2 mv squared here plus 1/2 I omega squared, because this has both translational and rotational kinetic energy. It doesn't have any potential energy, so this potential energy is 0. That equals kinetic energy at the top, which is 0, plus the potential energy, which is now mgh. Second line here, I have, this stays the same. I want to get this all in terms of v, or at least the same variables so that I can solve this. We're not actually looking for velocity here, we're looking for height. I don't know if I specified that. We want to know how high this goes, but same process. So since I've got linear velocity here and I've got angular speed there, or angular velocity, I need to make those the same. And I probably could have done it the other way around. I probably could have converted this to angular, but I'm just in the habit of making this linear. So I, remember, is 0.16 mr squared. So there's I. And omega is equal to v over r. So v equals omega r, and omega equals v over r. Just how we convert back and forth. So omega squared is v squared over r squared. And then on the right, I've still just got mgh. So a few things can be done to simplify this. Everything has an m. So divide everything, both sides of the equation, by mass, and we can get rid of all the masses. This r squared is in the numerator, r squared in the denominator. Those cancel out. And there are a lot of there's a 1/2 v squared in each of these terms, so I can factor out a 1/2 v squared from here and from there. This is 1/2 v squared times 1. This is 1/2 v squared times 1 plus 0.16. Oh, sorry, no, it's times 0.16. I'd already put this together. So this 1 represents that. That's 1 times v squared, 1/2 times v squared. And this 0.16 represents all this. This would be 0.16 times 1/2 v squared, which is what you get from that. I didn't explain that very well. And then I'm left with gh over there. I want to solve for h, so basically divide both sides by g. And cleaning things up a little bit, I'm adding these together to get 1.16 times v squared. This is all over 2. And then I divide both sides by g. So there's my formula. And then I just substitute my values in here. I guess I've already substituted this 0.16 in. So I have 1.16. There's my initial velocity I was given, divided by 2 times 9.8, which is g. Got to square this, and then I get 3.6 meters. Number 6, which, oh, is it going to recognize me again? Sorry. Something about the light behind me is making it difficult. I'm going to put in my pen. All right. Last one. Here's the problem, and so we've got a beam of given length, and there's a center of mass right in the center. You're given how much the beam weighs, so we're going to know what weight is acting there that's representing all the mass of the beam, but will be acting right there. There's an object hanging somewhere, some distance from the right. We're given the distance from the right, and we're also given the weight of the object. So people are going to have objects at different points along here. You're going to have beams of different lengths. You're going to have beams of different masses, but so those are the commonalities. What you have to do is tell where you should put the fulcrum in order to balance this beam in terms of distance from the right end. Now, my numbers that I decided to use look like this. I did this, again, a different way. So if you're thinking, hey, that doesn't look like mine. My weight was way over here. It's not really going to matter. You could do this the same way, and I'll show you what I mean in a minute. So in my particular example, the length of the beam was 11. The weight was 240 newtons, and it was 7.5 meters from the right end. The beam itself was 263 newtons, and I guess that's all I need to know. So in order to make this whole thing balanced, we need to have the torques balanced. And I think it makes sense here that I need to put the fulcrum somewhere in between this weight and the center, because the center is going to pull down like this, and this is going to, if I put it anywhere to the right of the center, then both of the things are going to pull it counterclockwise. It's going to fall. If I put this over here to the left of the weight, then both things are going to pull it clockwise. It's going to fall. And actually, you can do it this way and it still works, and I'll come back to that in a second. So in this particular situation, it makes sense to put the fulcrum in between here and here. If you don't, if you put it somewhere else, it could still work. But we'll talk about how to make that work. So I have to write an expression for the counterclockwise torque and the clockwise torque. So the counterclockwise torque, if the fulcrum is here, is going to be caused by this weight. So that's the force. Torque is force times radius. And the force is 240 newtons. I need to know this distance. So I'm saying x is the distance from the fulcrum to the right end of the beam. And if that's true, then this little distance right here is 7.5 minus x, because the distance from here to the weight is 7.5 meters. So this is 7.5, this is x, this is 7.5 minus x. So there's my lever arm for the counterclockwise torque. For the clockwise torque, this is where my weight's exerted. I need to know this distance right here. So the force, 263 newtons, this distance has to be x minus 5.5, because the weight itself is acting at the center of the beam. The length of the beam is 11. The halfway point is 5.5. So if this distance is 5.5 meters, this distance is x, then this little distance right here is going to be x minus 5.5. So there's my lever arm for this force. So multiplying these out, 240 times 7.5 is 1800. 240 times negative x is negative 240x. 263x. 263 times negative 5.5 is negative 1447. I add 1447 to both sides, subtract 240, add 240 to both sides, and then divide, and I get 6.45 meters, which is the distance from the right. Now, here's another way I could have done it. This is sort of impossible, but it works. So I said, what if I put the fulcrum over here? It's not going to work, because the beam itself, this is to the right of the beam center of mass, so the beam is over on the left of the fulcrum, pulling it down. So is the weight. This is just going to fall. But here's what I can do. I can say torque clockwise equals torque counterclockwise. And I'll just choose one of these two and say it's going to be the clockwise and one's going to be the counterclockwise. So I chose this one as my counterclockwise torque, 240. And the lever arm right here, this distance, is 7.5 minus x, because 7.5 was my distance from the right to where the weight is, and x is my distance from the fulcrum to the right end of the beam. Now the other one, even though that's to the left and it's going to be making things go counterclockwise, I'm going to call it a clockwise torque. And instead of using 263 for the force, I'm going to use negative 263. So how about that? Because it's actually a counterclockwise torque, but if I'm going to refer to it as a clockwise torque, I need to refer to it as having the opposite value. So you can think of this as 263 Newton force sort of in a counterclockwise direction, or a negative 263 Newton force in a clockwise direction. And the lever arm is 5.5 meters minus x. 5.5 is the halfway, it's like from here to the center of the beam, and x is this, so this distance is 5.5 minus x. And when I do all this stuff, I get 6.45 meters. So it's the same as when I did it that way.